Hello, this is Dr. Marina Wal Sabra from the Lebanese University. In this video, we are going to continue the chapter of binary combinational logic that we have started before. So we are at a point where we want to see how to implement a function from what we have called the canonical form or the minterm form. I have in front of me a table where I have the variable values in the standard order. I have the function outputs and I have the index. So I have the indices that we have used in the minterm form. So for index 3, this is minterm number 3 and it is values 0, 1, 1 for x, y, and z. And if I transform this binary value into decimal, it would give me 3. The function that I have implemented from an original function that's f is equal to x plus y prime z. And this function is the reduced form of the function that I have. So to create my minterm form, the function is deduced from the truth table by ORing all the minterms that have a value of 1. In the definition I added that I could also AND all the max terms with a value of 0. But I will not be working on the max term form because I want to work only on minterm forms in this video. So to OR all the minterms, I go in here, I see that f is a 1 for minterms 1, 4, 5, 6, and 7. So the minterm for this value, for the index 1, is 0, 0, 1. So the corresponding minterm is x bar or x prime, y prime, z. And I go for adding each one of these terms, that is x, y prime, z prime, x, y prime, z, x, y, z prime, and x, y, z. This is a long way to represent the minterm form, as we are going to use it more often. It is preferred to use either the index form or the shorthand form. The index form is column with the number of minterms. So this is minterms 1, 4, 5, 6, and 7. That we can also write in the form sigma of m minterms and list their numbers. So this is the shorthand form. To implement it, in here I have an example of the implementation of a minterm form and the implementation of the reduced form. So in the minterm form, we can see it is always, because it is a sum of products in the expression, it is OR and in the implementation, or is towards the output side. Where in the minimized form, it depends on the expression itself. In this case, it is b prime c or a. So I have an AND in here, and then I have an OR. As you can see, always the implementation in the reduced form gives me a smaller circuit. The implementation in the minterm form gives the largest, if you want, possible size of circuit. So it's by no way the reason why we work on minterms. Minterm form is not to be implemented directly. Minterm form is if I want to compare if two equations are the same, I can go to the minterm form and there, or to the truth table, of course, and there I can really compare all the possible values. So it is the expanded form and not the reduced form. For implementation, we talk about the cost criteria. In the previous example, we talked about the difference between a minterm form implementation and a function implementation, a reduced function. But what if I have two different functions that have reduced forms, two complementary for the same function? So there is a law to count a cost. So we have three different criteria and three different standards. The first one is to take the literals, that's to count the number of variables inside the expression. The second one is the gate input cost, which is the number of literals plus the gates. And the third one is the gate input with NOT. So in the second example, in the second method, we do not add the inverters. In the third one, we do add the inverters. This is going to be clear with the application in here, the example. So if I have an expression, this is f is equal to a or b and c, or not b and not c. So the first cost criteria, this is the implementation in a circuit of the same expression. I have 5 literals, so L is equal to 5. Whereas in the gates, I have to go in here either to the figure and add all the inputs to all the gates, or go to the expression and add all the ands in the expressions. So add to the 5 literals the 2 inputs that I have here, I get 7 gate inputs. Adding the nuts, B is inverted once and C is inverted once, so I have to add 2 more inputs to the expression, and I get 9. So I either compare on one of these between 2 different functions to see whichever has a smaller cost. Just to note that if I have B inverted twice, I should count it only once because the gate will be used only once. In here, there's another example. I have the same function and I have 2 implementations for the same function, 2 different ways to represent it. So we go for the first one. It is A and B and C, or not A and not B and not C. And this is the circuit that it corresponds to. I have 6 literals. I have 8 gates, gate inputs. And with the inverters, I have 8 plus 3, because I have all of them inverted, that's 11. If I go to the second method, that's the complementary method. It gives, if you want to go to the truth table and verify it, it gives exactly the same output. And the cost, it has also 6 literals, so in the literal comparison it's the same. In the gate number comparison, it has one more gate, one extra gate input, and in the gate and not, it has also one more. Therefore, it has a higher cost of implementation than the first expression. Therefore, we would prefer going to the first expression to implement it. And this is why we have to go for a method to reduce the expressions, so that when we implement them at the lowest cost. So in here, we are going to see how to develop or reduce an expression using 2 variables, 3 variables, and 4 variable expressions using K-maps. I have a reference book if you want to go into more details, because of course this video will not cover everything around binary numbers and around K-maps. We are going to take the essentials. And moreover, if you have a function of more than 4 variables, it will be a little bit complicated to use K-maps. So you could also go back to the binary logic expressions and reduce them if you want to reduce K-maps or reduce binary functions with a large number of variables. Forming a 2-input K-map. What is a K-map? A K-map is a table where I am going to put all the minterms inside. It looks like a truth table, or it has the same number of values like a truth table, but they are put in a way to be able to graphically reduce them. K-map is a graphical way of reducing a function that is complementary to the equations that we tried to skip in the first video. So we're going to replace them with this graphical method. So in here, this is the first variable, A. So it's the one to the leftmost in the minterms. This is the second one, and in each row and column, I have all the possible values, which are 2 in each case in here. I also can represent in the vertical way. So I have in here A prime and A. I have B and B prime. So I can either read them from the values or read them from the letter representation. If I want to fill in the values from a table to a K-map, I am going to go for the value that is represented in here. So A is 0, B is 0, so I take the first value and put it in here, and so on. I can also refer to them as the midterm index. So I have row 0, I go in vertical columns, I fill them column by column, so it's 0, 1, 2, 3. If you can, well, the values in here are 0, 1, 0, 1, and so I fill them back into the K-map. If I have three variables, it is a little bit more complicated. I have to pay attention that when I'm filling them up from the truth table, they are not straightforward, because here I have two variables, A, B, and C is on the other side. So to fill them up in the K-map in a way to be able to reduce the functions later on, I have to put 0, 0, 0, 1, 1, 1, 1, 0, and not 1, 0, 1, 1, because every time I want to move from one value to the other, I have to make sure that exactly only one of the variables changes the state and not both of them at the same time. So when I'm implementing from a truth table, this is going to be 0, 1, 2, 3, 6, 7, 4, 5. And as well, I can also see the variables in the letter form. So in all of these four squares of the K-map, I have A prime, so A is not. And in here, A, so A is true. And so on. In B, it is true in the four middlemost squares. It is false in the edges. And C and C prime, just like when I was with a two variable K-map. So how to fill it up? In here, we just said that you have to go and pay attention that these are inverted with respect to the truth table. So the first two values are here, the second two, the third two, and the fourth two. For a four variable K-map, I have four variables. I have A, B on one side and C, D on the other. If I put them in this order, when I'm filling up from the truth table, I'm going to go from the first to the last, column by column, paying attention to this one and to this one. So I have the same inversion twice. I have A is true on the two columns to the right, B is true on the two columns in the middle, C is true on the two columns to the bottom, and D is true on the two columns in the middle, on the two rows in the middle. So this is the four input K-map. So when I'm filling it up in here, I have to pay attention at every row and every column that is 0, 1, 3, 2, 4, 5, 7, 6, and then I go 12, 13, 15, 14, 8, 9, 11, 10. So you have to pay attention when you are filling them up. So how to minimize a function when you have a K-map? We have three basic steps. The first step is to look at the K-map and detect the ones that are there and put circles on groups of ones, paying attention that the number of ones inside each circle should be a power of 2. So it's either 1, 2, 4, 8, or 16, which is the whole four variable K-map. So I can never put a circle over 6 variables, 6 ones, even if they are forming a shape. The ones have to be either one above the other or one next to the other. They cannot be diagonal. The next step is to create a product term for each prime implicant, is to read from the table what the product is, what the term is. And the third one is to deduce the function by summing all these product terms on what we call the prime implicants of the K-map. So this is the first example on a two variable K-map. If I have this function, I have two adjacent ones in here, so I want to put a circle on them. Since the circle covers both ones, I don't need to add any more circles. The second step is to read from this. Since B has a value 1, throughout all the circle. Therefore, this value is equal to b. If you look at a, it takes two possible values, so this is not a variable that is sustained in the function. It is only b is equal to 1. So whenever b is equal to 1, the output function will be equal to 1. We can also verify it from the truth table. Whenever b is equal to 1, the function is in fact equal to 1. So because it is one term, the third step is skipped, f is equal to b. If I do this, so I take all the possible circles, I get 1, 2, and 3 terms. So this is an overlapping, this is too much of overlapping, and it makes the form not minimal, therefore it is refused in the reduction of a K-map. Once the ones are totally covered by a circle, I don't add any more. If I have a 3-variable K-map, a 3-variable function implemented within a K-map, and I want to reduce it, I can, this is how to reduce it. I will begin by trying to look for 4 variables. 8 is the whole K-map, so probably I'm going to look for 4 variables. So whenever I find a 4 variable, I'll choose it. Then if I have ones that are not covered, I will try to cover them with the largest possible circle. So instead of covering this one alone, and if I have covered it alone, I would be covering all the ones with circles. So the output function will be giving the same exact output. I do want to reduce the form, therefore I want to make the circle bigger. So this value, instead of being a bar, b bar, c bar, it is a bar, c bar, and this one is b, because here I can verify that it is b. So the total function, the global function, is f is equal to a bar, c bar, or b. If I have 4 variables, I am going to proceed in the same way. And here I have 2 squares of 4 that are covering the ones. And in here, this is b and c prime. And the other one is b and d prime, because d prime is true in here. Therefore, the function is equal to bc prime or bd prime. These are some more examples. If you see in this one, I have, I'm covering zeros, so this is an application where we are looking for the max terms. You can take the same example and look for the min terms. And here we have an overlapping. So I have in here the prime implicants, and what I have one of the prime implicants, this is the term, the circle, is covering ones that are already covered by other circles. So this is what we call a non-essential prime implicant. So I can remove this and the output function would remain the same. Therefore, the minimal function is going to be this term, which is a c prime, or this term, which is b c. And the term which is vertical, which is a b, can be removed from the expression. So we come in here to talk about prime implicants and essential prime implicants. So the prime implicant is the term that I get from the circle, and it is essential if it is the only possible way to cover this value, or the min term, the 1. So I don't have a standard method. The method to know them, differentiate them, is when we look at the K-map. So if I have this 4-variable K-map, and I want to cover it by prime implicants, these are all the prime implicants that I have. I begin by the largest possible circles. These are 4. And in here, this is a b bar, this is b bar c, and we have b bar d bar, which is the 4 corners, which is usually forgotten, so you have to pay attention to it when you have it in your K-map. but these are too many. So these are all the possible prime implicants that we have. Because we have ones that are only covered with um, only one prime implicant, this is what we call an essential prime implicant. So we have this one and we have this one are only covered by one prime implicant. Essential, this means I cannot get rid of it. I don't have a choice. I have to keep it. So I have to add two more prime implicants to cover all the ones. But I have the choice. I can either put a vertical one in here and another vertical one in here. I can go for a square of 4, and the vertical one I can go for a square of 4 here. So the other half, I have a choice with them. What about don't cares in a K-map? Don't cares are usually situations or values of the inputs that are never going to happen within the circuit. Either because the combination of the inputs doesn't allow it, we are talking about implementation in real life machines and real life situations, or because the circuit itself doesn't allow to have this output or this combination of inputs. For example, if we have a circuit with an enable, when it is disabled, the enable itself is one of the inputs. When it is disabled, I don't care what the other values are, the output would be none. So if I have a table in here with several inputs that are already indicated to be don't cares, when I want to implement, I don't care if I take them equal to 1 or I take them equal to 0. So instead of considering them all as zeros and taking the value as here as a prime CD, I can make a larger square, a larger circle, and implement the function which would be reduced with respect to this one. So this is where I'm going to use the don't cares in our K-map reductions. And here we have several exercises that I expect that you go over them on the slides and do their solutions. Thank you for your attention.